Hi, everybody. Last lecture class. Yay! Which, of course, means next week is the final exam. Dun, dun, dun. Does anyone have any questions on anything before we start up today? Okay. Well, I got a couple interesting things to talk about. There's actually one thing I forgot to talk about last week when we were talking about inline functions. Um, let's take a little example here to start with. Let's say that I have a list and we'll say that he has some mixed content in him, something like that. So first of all, what do you think the type of that list is going to be? Any ideas? Guesses are okay. I heard an attempt. Go ahead. It's okay. Yeah, the actual type of list. If I were to put a type declaration after this, colon something, what would that something be there? Exactly. List of any. We got to find the common super type of all these guys, and the only common super type there is any. Now, if I remove that and then I float over list, we'll see that it tells us that he is he went a little bit more interesting, that comparable and serializable. So yeah, I don't want to get too much into that. That's basically that's when we were talking about generics, we had that when clause that was bringing in conditions onto the generic type. So what this is doing is this is saying it knows that everything that's in that list is comparable and everything in that list is serializable. And so it's actually pulling those two together as kind of a join type. Um, so if I threw in something a little different, like if I had a class person and then put a person in there, it should be any. Yeah, there we go, list any. But you'll see the compiler was actually pretty smart. It was able to say, hey, there is some common supertypes that are not any. So I'll pull those together. So let's say I have this list here. And maybe what I want to do is filter it out. Now there is that list dot filter is instance that we've seen before. Um, I want to kind of show you how that one actually works and where it comes from. Let's start off by actually seeing what the code would be inside of that filter is instance function. So if I said like val new list equals mutable list of, and I'll give it a type any. Let's say we're filtering it to a string, just strings. I'm going to create a list to store things in, and then I can say for item in list if item is string, then I can say new list dot add item. Note the smart cast that's happening there because we're inside that. And then if I do a println on the new list, I should see just the A and the B printed up there. So let's take a quick look at him. There we get the A and the B. So this is kind of what would be on the inside of that function that's going on. Pardon me 1 second. My daughter's sending me pictures of food. That's what I need right now. So this would be basically what's inside of that filter function. But let's see how we can write that filter function. What if we tried to say fun list any dot filter is instance, and we got to have some kind of parameter there. We'll think about that in a minute, and that's going to return something that's a certain type. So we're going to need to make this a generic function. So we're going to have a t. Now, taking a look at the type of things that could be inside that list of any, t would have to be a subtype of any. Now, if this list could contain nulls, any question mark is automatically the super type of any generic parameter, so you wouldn't need it, but we probably would want to have nulls, so we just have to explicitly say t is any. Now the question is, what do we do with the parameter on this guy? Well, we're going to need to pass in the type that we can compare it to. So I'm going to call that class, and it's going to be a K class. I'm calling it class instead of class because class, of course, is a reserved word. And we'll do something that looks kind of like that. The return type is a list of T. And then we can come up here and grab all this, paste it in. And now we're going to notice something here. We actually have to deal with the type that came in. So if I try to put in class, that's not going to work. If I try to put in T, that's not going to work. Wait a minute, why is that working? For item in this, there we go. Now it's not working. Okay, it was thinking that it's working because it wasn't getting that far in the compilation. But we'll see here. It's like you can't check for an instance of an erased type, and what that means is that this function loses all knowledge of what T really was when we did it at compile time. It gets wiped away or erased. So all we know about it is that it's some type. And so you can't just check against some random type. You need to actually have a concrete type. That's where this parameter here comes in. We're actually passing in a type to say what the type is. Notice that it actually is of that T type, which associates this class with the result on the end. So nice generic fun there. So we can't use this syntax like that. It just won't work. It's going to look here. It's going to say, hey, you have to have actually a type reference there, and it doesn't know what class is based on a type reference. So we have to change this a little bit to say if class is instance item. So we're kind of reversing it around. We're going to say, is the thing that I'm passing in an instance of this class type? And that class type, the K class, is just metadata describing the class that something is. So this will do that check for us. But now we go down here and it says new list add item. If I float over item, the smart cast doesn't happen because the compiler can't figure out at compile time what the type of that class is. So what we need to do is we need to explicitly come in here and say as T so that the compiler will be happy. We're telling it, hey, cast it as whatever type this was used as. But if we float over this, whoops. Oh, here's a problem there. Let's put him like that. There we go. So we're making the compiler happy by putting that, but the compiler is saying, you know, I can't tell for sure that that really is a T at this point. All I know is that it matched some class that came in, which might not be T. Now looking at the declaration here, it looks like it should be, but the compiler can't figure that out based on this function call. So what we need to do is shut the compiler up here and say, add unchecked cast there, and now poof, this function works. And we need to, of course, return the new list at the end here. Let's see what happens if we say println list filter. Oh, what did I call this? Let me call this my filter, just so we make sure that we're definitely calling our stuff. And I'll call it number 1. And we're going to pass in here string : class. So there's a few things I don't like about this. It works, and if we run it, we should see that printing out A and B as well. Yep. It works, but there's 2 big things I don't like. One, this whole unchecked cast thing. It's really awkward. It'd be nice if we can avoid that. And 2, this syntax is super, super awkward. It really doesn't flow as nicely, and you got this extra : class floating around. I'd like to get it to the point where I can say this, just like we had in the real filter is instance. That's a little bit nicer syntax that we have there, and depending on how it's being used, we might even be able to get rid of the bracket, string bracket. So let's take a look at this function, what we can do with it. Let's say instance 2. So we know we don't have a parameter coming in. What we need to do is do something special with the generic type that we have here. We need to add the word reified in front of it. And what that means is I can really treat this as a type, and I'll know what its type is. The only way we can do that, though, is if we inline the function. So by doing this inlining the function, we essentially come up with exactly the same stuff that we had before. See how it's actually, being inlined? We can use this is string because when the function gets inlined, the reification of it just basically replaces t there, and then life is peachy. So I need to kind of convert this back a little bit and say if item is t. I can get rid of that, and now I don't even need to do that as t because I'm getting that smart cast. So you notice that this code here is exactly the same as the code that was right up in here for creating that list. And I can do that because this inline throws it in place and then replaces that t with string. And so item is string is perfectly fine statement. That'll work. Now, the thing you have to be careful of is if your function gets really big, the inlining is going to pull in a whole big chunk there. So one thing we can do, let's say that the function was really big. We'll just say the function is really big. Actually, I want to, we'll call this number 3. So what I want to do is cut down the size of this function. And the easiest way to cut down the size of a function is to factor out part of the functionality or all of the functionality. So if I take that, and let's come back to my first example, and put him in, and let's say that this is going to be filter is instance 3a. So we're going to keep that exact same stuff that we had to start with, but we're putting a reified function in front of it. So we're just going to take this guy and say equals my filter is instance 3a, passing in t, : class. Boom. And when this is inlined, that t will become string : class, which is exactly what we had for this call before here. So this gives us a way to use the nicer reified syntax from the caller, but still have more complex function behind the scenes that we don't want to inline. And that gets even more important if you have a recursive function behind the scenes that you want to call, because you can't inline a recursive function. I believe you can inline a tail recursive function. I really don't want to get into tail recursion because that can go down a rabbit hole really fast. But just as a little note, depending on how you write your function, if the very last thing in that function is a recursive call, you can put the keyword tailrec in front of it. So you could have tailrec fun, blah, 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 blah. And then inside here, maybe we had the tail recursive call. Let's see, what is he saying? No tail calls are called. Let's say n : int. If n is greater than 0, n minus 1, something like that. I believe that'll work. There we go. So what this function is doing is this one is basically just kind of working its way down to an n equals 0. And until it gets to the n equals 0, it's just always going to call itself recursively. Anytime you have a tail recursive function, so where the recursion is the last thing happening, it can automatically be unwrapped into a loop. And that's really about all I want to say about it. So depending on how you write your function, if you write it in a way that the recursion is the very last thing happening, it can be unrolled into a loop automatically. And I'm pretty sure that this one can be inlined. Maybe not. No, it won't let you inline recursive functions at all. I'm kind of surprised because you'd think with the tailrec function, which actually gets converted into a loop, it can be inlined. Now think about this function for 1 second. What is the advantage to doing this tail recursive and letting this get unrolled into a loop versus just plain using an old recursive function? What would the advantage there be? Any ideas? Less stack overhead, and you don't have the chance of blowing your stack. In a case like this, if I had, like the X, triple X was passing in a billion or something like that, this could blow my stack. If I have it at tail rec, what it's going to do is set it up as a loop, and it can just loop through that billion, and everything's perfectly fine. Okay, so I really don't want to talk any more about the tail recs, but just keep in mind that's something that may be useful. it can be a real pain to try to write something in a tail recursive manner. Usually it involves setting up an accumulator. So you'd have an extra parameter that kind of keeps track of the result so far. And you add to that result, whatever that means for whatever your function is doing, and have that be the last call, kind of similar to this, where you just say, if I'm not all the way done processing my data, do this. But let's take a look at this this reified function for if we had a recursive data structure, and I'll just use a binary tree here. Let me just copy a little code here. Yeah, that should work. So here's a little binary tree node definition where he's passing in some name for the node, a left and a right, which default to nulls. And then I'm just having a couple functions for walking through it. Well, let's take a look at the insert first. So the insert function on this is basically going to insert anything that has a lower name than our current name to the left, higher name to the right. So pretty standard sorted binary tree situation here. So here I'm just saying, if I have a left, call insert, otherwise set the left. If I have a right, call insert, otherwise set the right. So it just recursively calls this function to go down there. Now for an in-order traversal, a really simple one here, we just say if we have a left, call in order, print ourselves. If we have a right, called in order. This one here is kind of a filtering in order. And what this guy is going to do, he gets that class passed in, just like we were talking about before, and then process the, whoops, process the left, process me, process the right. And the process me in this case is doing that check. Now, because this is a recursive function, we can't make it inline. And because we can't make it inline, it's going to be it can't have a reified on it. So what I'm going to do is I'm going to make this one private so that nobody else can call it. I'm kind of hiding this as the real processing behind the scenes. And then I can throw that nice little inline fun reified t. And then we'll have this guy, what was I thinking? Oh, in order. Wow, my brain just kind of farted there. I'm going to call this in order 0. That's going to be kind of my stuff behind the scenes. Oh, I should probably mention why this even matters, because I only had this node, right? If I had different types of nodes, so let's say that I had these guys. So if I had like a person node, a place node, and a toy node, which have different types of data, I'm basically storing a heterogeneous data inside of a tree. And I might want to filter it out to say only give me the persons. Let's just make sure that works first. Go up to my main. And I had some sample data up here. So this is just some sample data. I'm just doing a bunch of inserts on a bunch of different stuff. And let's do root.inOrder to print out stuff and just see what happens. So here's my stuff coming out. These are all my nodes. Notice they're all in alphabetical order, which is exactly what we wanted. And then I can call the other guy, root.inOrder, passing in, let's say, person node, : class, just to limit it. Oops, too many arguments. Did I? Oh, I made this private already. Let's just do this just to make sure it works. And we'll run him. And now we're only getting people coming out. So we had Mike, Scott, Sue, Trevor, it looks like. Yeah, so Mike, Scott, Sue, Trevor. I should really put a little separator in there. just so that we can actually see. There we go. That's better. That's exactly what I want. Okay, so we know that that function is working just fine. Let's create that little reified thing. So what I'm going to do is I'm going to hide him because I don't want people using him directly. And it would be okay if we left him up, but we can just hide him like that. And then we add this inline fun in order, and he has that reified t on him. And this guy is just going to call in order, passing in t, : class. In order 0. And what doesn't he like here? Oh, shoot. I forgot about this piece. So what's happening here is you can see it says public API inline function cannot access non-public API function. And that's because this inline function, it's going to replace this call at the caller location. Now there is a way around this, and I am trying to remember what the annotation on it is. Published API. So what we can do by saying @published API, is this the one here? Only applicable for internal declaration. Oh, that's right, we make it internal. There we go. And now what's he having? Too many arguments. I get to rename this guy. If we had kept this public, we wouldn't need to worry about this, but what published API does is it says only let inline functions call it. I believe that was how it's worded. Let me see. Yeah, allows you to use it from public inline functions, which effectively makes it public, but it hides it from people directly calling it. So if we look up here, we'll see that we can't directly call it anymore because it's public, it's internal. Can't call. I'm going to say internal / published API. Can't call from outside a inline function. And that published API annotation was explicitly defined for this case, so you can put a front end on something that's doing more complex stuff. So we're going to get rid of him for a minute, and let's just reword that. We'll change this to say root in order, bracket, person node, like that. And compile-wise, you can see that that works just fine. All he is a really simple front end that converts that reified t into the t : class so that my caller can just use the generic syntax as opposed to passing the class in. There's a couple other scenarios where it might be a little more complex, but that's the most useful way this is, or the most common way this is used. So if I run this now, oh, what is he saying? In order defined, reified, unit defined, platform declaration clash. Oh, it's because of the type erasure. So because of the type erasure, in order paren looks the same when it gets compiled as this one here. I mean, they basically have the exact same signature, so it doesn't know which one to call. So let's call this print in order. And then we can come up here and change this to print in order. You'll notice before I do that, that person node now is no longer valid there because that in order function doesn't have a generic. So we'll say print in order. And now let's try running this. And there we go, we get the same results. Okay, any questions on that? So reified it just gives you kind of I think it's a cleaner look for how that is. And depending on where you use it, you can help isolate where people actually have to use : class. That's all it's doing for you. Okay, so let's do something else that's going to be kind of interesting. What was this? Oh, that's that guy. Okay. So what I'd like to try is setting up a code generator in Kotlin. And Kotlin has this concept of something called a symbol processor. And before I talk about that, let me kind of step back a moment to Java. And Java had these ideas of annotation processors. And what you could do is define an annotation, which is basically just some metadata that you explicitly set in a class, and it'll generate things for you. So for example, let's create an annotation here and just kind of show you what that part looks like. I'm going to create a new module. This is a completely independent compilation unit, and he's going to contain my annotations. I'm doing this because I'm going to create an annotation processor inside its own module. And I want my base code here to be able to see the annotations as well as the annotation processor. So it's going to be a shared thing. So I'm just going to call this annotation as my module. And Kotlin Gradle, blah, 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 advanced settings, Java dude, that looks good. Create. So we'll see inside this, it's now created this annotation module. You can tell it's a module because there's that little blue blob next to it there. Although that blue blob also is for main and test, which aren't modules. Well, that's helpful. Yeah, I don't know why they're using the same icon there. That's interesting. So inside here, I'm going to get rid of that main.kt. I don't need him. But I'm going to create a package in here that I'm going to call com Java dude annotation. And I'm going to define an annotation class in there. Let's call this generate logging. And hopefully I'll be able to get this example working. I had a slightly different example that kind of worked, but it was doing some really awkward stuff. I was kind of basing an example I was playing with on an old annotation processor I wrote in Java. The idea of those annotation processors in Java is it could take a look at compile time at the annotations on some classes and then generate code based on that. Or if you wanted to, have it report errors, things like that. What I'm going to try to do here is set things up so that we can add an annotation on a class and have it automatically generate a wrapper that when you wrap the class with it will log all of its functions. So I'm going to make this be an annotation. And that's basically all you need for an annotation definition. Annotation class, generate logging. In Java, you'd say @interface, which was super awkward. But it was one of the few things they could do without having to add a new keyword to the language, because you really don't want to add new keywords to the language. It can blow people up. Admit somebody there. Okay. Now with an annotation, you can limit where people can use that annotation. It's weird that it's got all that space. And so I'm going to, it's the get notation there. So I'm going to put on this that I want this one to be targeted to, look for my, sorry, I want to take a look at annotation target was the name of it. I want to target it so that it can only be used on classes. You can set it up for all sorts of different things. You can have it be set up so that it's targeted at the top of a file. It's on any type, which would also include enumerations and interfaces. It can be on an expression or a field, a local variable. You can basically say where this annotation is applicable. For this particular example, I just want it to be applicable for a class. Now, if I was really implementing this, I'd probably want to be more general and let it also apply to interfaces. But I believe if you say type, it will also apply to enumerations, which gets a little trickier. I'm going to wave my hands at some of this. We're just going to go for a very, very simple approach here. I'm not going to take into account anything on generics. I'm not going to take into account functions with return types. What I just want to do is generate a wrapper that calls functions and has a little thing that says that prints out I'm calling a function. So I'm going to attach this at the class level, but then I have to decide how long this annotation sticks to the class. There's a bunch of different retention functions. So I can say annotation retention, source, binary, or runtime. Now what source means is that it's not kept in the compiled output. It's only going to be visible on the source, only accessible during compilation, during the Kotlin symbol processor phase. Binary means that it's also going to appear in the generated output. So in the bytecode file. And that means that at runtime, you could look this up. And sometimes it's useful to attach an annotation to a class or a function or whatever for use to look up at runtime using reflection. And then you could do some interesting things with reflection. In this particular case, we're just going to stick it for the source. I'm sorry, binary doesn't make it available at runtime. Runtime makes it available at runtime. Binary means it's in the jar. It just doesn't get visible through reflection. Runtimes means it will be visible in the reflection. I'm just going to say source. I want the annotation to go away after it's been processed. So this guy I can now attach to anything I want to. So if I come in here, I've got this annotation module. In my overall top level build.gradle, I'm going to add a dependency on that project so I have visibility to that annotation. So I'm going to say implementation project :annotation. And the colon just means it's a submodule of my current project. So I'm going to pull in that code, whatever's inside that annotation module, as something I can use as an implementation dependency. Now, if instead I had said API dependency, what that means is that everything that's inside annotation gets exposed if somebody uses this current module. So if, let's say that I had module A, B, and C, and module A uses module B. If I set up B as an API implementation, sorry, API dependency, and module C pulled in A, let me write this down so that it actually is, you don't have to try to get it in your head. So if I said A uses API C and B uses implementation A, B can use everything public in A and C. If instead I said A uses implementation C, B could only use the stuff that's public in A, because C doesn't get published as an API as part of A's API. Hopefully that makes a little bit of sense. Most of the time, I'm going to say nearly all of the time, use implementation. And the reason for that is that if you have implementation dependencies, B doesn't care if anything in C changes, only A does. So if C changes its API, only A needs to be rebuilt. So the more implementation dependencies that you use, the easier it is for the build system to say, I don't need to worry about building as many things. I only need to worry about things that are directly dependencies of mine triggering a rebuild. Hopefully that made some sense. So we're going to use this implementation one here. And then I'm going to click on my little elephant up here to reload the Gradle changes. That lets the IDE understand that these dependencies are available. And now if I take a look underneath my source main Kotlin, I'm going to create a new package. Oops, let me check something before I forget. Okay, he came up as com.javadude annotation. Sometimes it'll say com.javadude.com.javadude.annotation, which is weird. I don't know why. So we'll say com.javadude.sample. And then inside there, let me create a class. Let's call it repository. Yeah, see how it generated the com.javadude.com.javadude? I don't know why it does that. So with this class repository, I'm going to throw that annotation on here. I'm going to say @generate logging. Notice that it's visible here because we reloaded that and we have that implementation dependency. And so now, if I write an annotation processor, I can find everything that's set up with generate logging and then generate some code that could be a wrapper around him. You can't modify the class itself that's being generated. At least I'm pretty sure with KSP you can't. With Java annotations, you definitely can't. With KSP, I don't think you can. I believe you have to go to an actual compiler plugin, which is a lot trickier to do. But cool stuff nonetheless. So what we're going to do is we're going to set it up so it's going to generate a wrapper for it. And I want to set this up so that I can specify the name of the wrapper for him. I'm going to say logging repository wrapper. Why not? We'll be nice and verbose on it. Now it's not working yet because I haven't set that up as a value on generate logging. So I'm going to come back here and change this to say name string. And now we see that everything's perfectly fine. He can take that name. So I've had some metadata set up here. Now I want to create a processor for it. So I'm going to create a new module up here again. And I'm going to call this processor. Let's call it logging processor. And blah, 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 advanced setting, com javadude dot logging processor. Why not? Okay, and once again inside there, I'm going to get rid of that main that was generated because I don't want him. I'm going to create a new package in there, com.javadude.logging processor, kind of like that. And we're going to create a couple things inside there. I'm going to create a class called generate logging processor. And you'll see this is kind of a common way of naming these. You take the annotation name and you throw processor on the end. It doesn't always work that way because sometimes a processor, you might want to have it act on multiple annotations. But if you're just having kind of a one-to-one where a specific annotation is handled by a specific processor, usually you'll name it this way. So to make him a class, and he came out okay. See, that one came out okay that way. That's weird. And so now I'll create another one in here. And I'm going to call it generate logging processor provider. So you need a processor itself and something that creates the instance of the processor, passing in whatever data you need. So I'll create this guy. And his package name's okay. I don't know what's the problem with you, Android Studio. You're weird. Now what I'm going to need to do is I'm going to need to pull in some dependencies here so that I can actually create this processor. So inside of the build for the logging processor, I'm going to need, first of all, those annotations, because I'm going to use those annotation classes. So I'm going to say implementation project :annotation to pull him in. But I'm also going to need the Kotlin symbol processor API. So I can pull that in just kind of like that. Note that the symbol processing API is specific for a specific version of Kotlin. One of my biggest gripes with Kotlin right now is that the compiler API and the symbol processor API are still experimental. They're still like under development. So they can change from version to version. That can make things a pretty big headache, but that's the way it is. Now it has to match up with the version of Kotlin that's coming in. Now notice up here I'm just saying Kotlin VM. I don't give a version number. What I'd like to do is at the top level of my project, specify the versions, and then that version is automatically used for any submodules that don't specify a version. However, if a submodule does specify a version, it has to be the same version. Now notice here that this says 22. I want that to be 23. So that's pulling in it's matching up the right version there. So now that I've got those in there, let me just make sure I don't need anything else. I think that was it. Yeah. I'm going to, again, hit the elephant to load the changes into the IDE. And now I should have available to me when I'm editing this API processor. Wonder what he's complaining about there. Syntax highlighting turned off because and it wasn't letting me see the message. So now this will give me the ability to get to that API. So I can come in here and say symbol processor as a superclass, which is defined inside that library. So I'm going to implement the process function inside there. This is the what to do when I'm processing symbols. Exciting, huh? The logging processor provider is going to have to be symbol processor provider, and I can implement him. He has a create function, and this create function is going to create an instance of the generate logging processor. So here I want to actually say return generate logging processor, but I'm probably going to need some parameters passed in. This environment that comes in gives me access to things like a code generator, a logger, and whatever options were passed in. And you probably want to pass those guys in there. So I'm going to say environment.codegenerator, environment.logger, and environment.options. Now we might not use all those. For this example, we're just going to use the code generator, but generally you're probably going to pass those three in. Now, of course, they aren't defined in the processor, so if I click on this and Alt-Enter, I can say Add Parameters to Constructor, boom, and hit Refactor. And if we go back to our logging processor, we now see that we have those extra parameters. I'll just clean things up a little bit here. There we go. So the provider is going to create the instance of this processor for us. In order for this stuff to work, we need the environment, in this case Gradle, to understand that we have these processors defined. And so what we need to do is set up some metadata in the jar file that's going to be created for this module that tells it that anybody's loading this jar, I have a symbol processor. So in order to do that, let's go back over to this logging processor module. And we notice how we have source main resources. This is a directory that when you're doing just straight Kotlin code or straight Java code, will dump whatever's in resources at the root of the generated jar file. So what I'm going to do is create a metadata directory underneath there and put a certain path in there that's well known. This well-known path can then be read by Kotlin, or sorry, by Gradle to understand. I should actually say be read by the annotation processor, the symbol processor. Let me get the right words coming out of my mouth. So that it will know that you have these processors in there. So under resources, I'm going to say create a new directory called metainf. And inside any jar, this is a very common metadata directory. And underneath there, I'm going to create another one called services. Again, another well-known directory that says, here are services that this jar provides. Any environment that understands these services will take a look in here and see if their specific service file is in there. Now, the specific service file that we have, let me get the name here because it's lots of fun. There we go. I'm going to say new file with this nice long name. Com, Google, DevTools, KSP Processing, Symbol Processor Provider. So this is the name of a file that the KSP processor will look for in the jar to tell it what provider is available. And I think you can put multiple providers. I'm not positive on that. I've never actually created one that had multiple providers. So inside there, we're just going to put the name of that processor. So the generated, is it going to like this? Oh, I can just hit Control Space. The generate logging processor provider. Boom. So I just put that fully qualified class name in there, and now KSP can understand that if it sees this jar, it will have access to a provider that it can use to create the actual logging processor. Okay, so far so good. So any questions so far? Now, this one's going to go kind of fast overall, but I really wanted to show you that this is an option. If you ever have something that you want to do with your code to actually generate more code, or even just analyze the code and report if there's errors. Instead of generating code, you can actually use the logger to say, hey, there's errors, and have it crash the build. Okay, so we have him. That should be good. Let's go to our logging processor. And if I'm lucky, I'll be able to get this to work. Okay, so So inside this process, we have this resolver class here. And this object is going to be able to let us find things that are annotated with certain annotations. So I'm going to come in here and I'm going to say resolver dot get symbols with annotation and pass in the name of the class that we're dealing with. Now, what's interesting here is that the symbol processor is not really a compiler, so it doesn't have all of the classes in your environment set up. So a lot of what we're going to do here is use some objects that represent classes and represent types instead of the actual real types that are being compiled. So here we're passing in a name here. So I'm going to go to my generate logging annotation, copy the package name, and then say copy the annotation name. So we're going to look up any symbols that are inside here that are annotated with that. Now, because we only allow classes to be annotated, we should expect this to just be classes. However, the compiler doesn't know that. All the compiler knows here is that we're returning a sequence of something called KS annotated. So it's something that the Kotlin symbol processor is annotated with, or a Kotlin symbol that's been annotated. We want to make sure that that actually is known as class declarations. So I'm going to do a little filter here, which is I'm only using this filter to let the compiler know what the types are. I don't have to explicitly typecast these. So here I'm going to say it's going to be a KS class declaration. And so now the result of this, if I took a look at this, this guy is a sequence of KS class declarations at this point. And it should be exactly the same things that came out of here because of the types that we were looking at. Now, once we have that, I'm going to take a look at each class, and for each class that has those annotations, generate another class. So I'm going to say dot for each. Actually, let me just say class declaration. And so inside of here, now I have this class declaration object. What I'm going to do just to start with is set this up so that we'll generate a class that's based on this name before we go digging through all the details. So what I'd like to do is say code generator. Oh, I didn't make these vals. So we'll say code generator dot create new file, and we're going to pass in a couple pieces of information in this. So we're going to say there's a dependencies object, and this actually brings in other dependencies if you need them. I'm just going to say false because we don't need anything else. And then we need a package name and then the class name that we're going to generate. So the package name is going to come out of, let's actually do that here. And we will say class declaration dot package name, which note that this returns a KS name object. So we need to actually just grab some sub information out of there. So I'm just going to say get qualifier, and that'll return us a string. So now I can pass in the package name. And there's an article I can point you to that really talks about these a lot better. I'm a little hazy on exactly which ones are which. So just, the example that I'm working with is really all I can do right now. I used to be really good with Java annotation processors, but there's a bit of a pain with this kind of indirectness on types. So we'll pass in our package name, and now we actually need the file name. So I'm going to base that on the class declaration that we have. And I think that's what I wanted to do, right? Oh, actually, no, I want to get the file name out of the annotation. So the annotation that was attached, this generate logging, has a name inside of it. So I need to pull that guy back out. And I can do that here. Class declaration, get annotations by type, generate logging. And this is an experimental method that they have that uses this to try to uses an actual type to make the lookup a little easier. It's still doing this kind of weird name lookup stuff behind the scenes. I'm not sure why they don't have an experimental one at this level as well. But hopefully eventually they'll get their API sorted out. Because of that, I need to explicitly say that I'm opting in because it's an experimental API. So I'm going to hit Alt-Enter on there and say opt in, and I can put it at any given level here. Yeah, put it at the process level. Kind of surprised that it doesn't let me put that at the statement level, or does it? Oh no, I can put it at the statement level. So I'm just going to put it at the statement level there. So that's going to give me the annotation that actually has the name inside of it. So here I can say annotation.name. Boom. And if we look at annotation here, it says it's of type generate logging. Okay, any questions so far? So this will create a file instance for me. Oh, my monitor is trying to shut down again. Weird. What I need to do is take this file, wrap it with a writer, and then, well, actually creates an output stream is what the create new file does. I'm going to take that output stream and convert it into a writer, because remember, output stream is binary, writer is a text output, and then I can write to it. So I'm going to wrap that in an output stream writer, which is a converter from a stream to a writer. And then I'm going to say .use, and if you remember what .use does, he says, make sure that I close this thing no matter how I exit. If things work, if things get an exception, no matter how I exit that use block, I will always close that file, or close that writer. I call that output. And then inside there, I can just write out whatever I want it to. So I can say output.write, and we'll use our nice little, actually make this be a trim margin, and do this, and bump, bump, something like that. So inside here, let's have the package name. So that's my package name statement. And then I'm going to be generating a class here. So let's generate a class with that name in that same package. So we have the right package. We need annotation.name. And I'm just going to put curly braces around him. And that's it for now. So hopefully this will generate a class, and we can take a look at that and see if it looks like what we want. And let me get rid of this to do, because otherwise this thing's going to blow up. Whoops. Oh, I need to return a list of annotated stuff to keep processing. So this thing can be a multi-phase process. So it could process, generate some stuff, and then I could say, hey, run the process again, because some of the stuff I generated has annotations in it. And I could repeat that multiple times. In this case, I'm just going to return empty list, because there's no second processing round that I need. Okay, so we have him. I think we should be in a good shape here to have this thing run. So I've got my repository. I'm going to use this main just to be able to launch this and make it rebuild. So it ran that. That means everything went okay. Let's take a look in our top level. I'm going to collapse a few things here. In our top level build, let's take a look underneath Oh, I didn't include the processor. That's the thing. So if we take a look at this top level, build.gradle, I didn't add in support here to say that I could be running the Kotlin symbol processor. So I need to add in a plugin up here to say that I want to run the processor. Let me copy that guy. And I believe I need this piece. There's the Kotlin Gradle plugin, which is going to, not sure why I need to specify that explicitly when I'm specifying KSP and JVM up here. I'm going to have to look up why this is necessary, but it told me to put it in. So that sets it up so that we can use KSPs, so we can use symbol processors. We just need to add a dependency to say which symbol processor we're going to use. So I'm going to say KSP, and then project, colon, what did I call it? Logging processor. Now note that KSP is red because I just added this and I haven't yet resynced the Gradle file. So I'm going to sync that Gradle file again. And now we'll see that KSP is okay. Logging processor looks okay there. Let's try building. And now let's take a look. You notice underneath build, there's a generated directory. And if I come down here to logging repository wrapper, which got generated for me, boom, we have class logging repository wrapper and package com.java dude. Yay, generated code. Excitement abounds. Now what I want this to look like, I don't know if it's going to let me edit this. Yeah, I guess it will. I want this to look like something like this. And then whatever functions are in that repository, I want them to appear here. Let's go to repository and add a couple functions in. So I'm going to say save, I don't know, person. And then maybe, actually, let's have him actually print saved, delete person. Deleted. And so what I'd like to do is have the wrapper call these, but have some logging functions before they're actually called. Let's just, for grins, put in a private function as well. Just to make sure that doesn't get included. I only want to do this for the public interface on this, because that's the only thing I can access. So let's look at these two functions. And what I want to have generated is going to be println running save, running delete, and then call wrapped dot save, passing in the person. Oops, we need to make that a val. And then wrapped dot delete, something like that. So I want to kind of have it look like this is what it should be generated. Now, I'm going to make a copy of this because I'm going to lose it as soon as we rebuild. Let me put that in my processor for the moment, just in a comment so we have that. Something kind of like that. And now notice if I rerun this and take a look at that wrapper again, the wrapper is now empty. It regenerated it. So you never want to edit the generated code. Let's go back to our processor and see if we can kind of work our way toward making this happen. So we want to generate something like this. Let's first of all take care of that parameter coming in. See if we can get that to work. So we're going to put in a paren, and we need to get val we'll just call it wrapped always, and then the name of the base type. So I'm going to say val wrapped, and then that base name of the class that we're currently working in. So I'm going to say class declaration. Whoops. And let's see, what do I want to use for that? I really had to kind of tinker around to get something that produced the right name. So it should be like class declaration qualified name, which returns a KS name, and then we'll convert it to a string. Now that's possibly nullable, so I'm going to put a question mark in there. We should process that and say, hey, if it doesn't have a name, we're toast. But I'm just going to assume that it's okay, otherwise it'll print the word null. So let's try this now and see what comes up. There we go, wrapped com javadude sample repository. Now we can be nicer about this and set things up so that we keep track of all the names that we've referenced and generate imports. For now, I'm just going to go ahead and keep these as qualified names. When you're doing this, it might actually be a good idea to keep qualified names in case there's any conflicts. And that way you don't have to have it try to be smart and generate aliases for them. So that worked pretty well. We should be able to use this now in our main. I should be able to say val repo equals repository, and then val wrapped equals logging repository wrapper wrapped around the repo. So boom, there we're using the generated code. That works just fine. So now we actually need to generate those functions so it'll do something. Because right now, there's now nothing that we can do with the wrapped. It doesn't have any functions other than toString hashcode and equals. So we'll go back to our processor. And what we need to do now is inside of here, generate the functions. So I'm going to create a little helper function. It's going to be an extension function on the class declaration to create that list of functions. And so I'm just going to call it functions here. We need to actually do something with it. And so what we'll do up here is say val functions equals class declaration dot. Actually, I can just go ahead and say class declaration dot functions down here. See if I can make this work. It's a little different than what I was thinking of, but I think I like this a little better. So I'm going to create an extension value on KS class declaration called functions. And that's going to be a string. And then I'm going to define a getter that's going to return something, which is going to be that string when I actually make it. So let's see if I can set this guy up. So I'm going to say get declared functions. Now there's there's a little bit of difference here. There's one that says get all functions, and there's another one that says get declared functions. Get all functions includes stuff that's inherited, whereas get declared functions are just ones that I defined. So I really just want to use my defined functions. I'm going to filter that based on functions that are public, because I only want to do those. Those are the only ones I can access from this wrapper anyway. I also want to, I found out when I ran this that actually included constructors. So I want to say no, not constructors. That doesn't make any sense. I have to have an object before I can wrap it. And then once I have that, I'm going to map all those functions into actually I can just do a join to string instead of using a map. I'm going to join to string, separating the functions with a new line. And I'm going to pull all those functions together. And this will give me a whole set of functions that I can now drop in place right there. So now I just need to say, well, what do these functions look like? So we're going to go up like that, pull these guys in, and we'll say fun. We need the function name. Simple name. There he is. And then I think is a simple name as string. I think that's it. We'll see how that works. I might have to do something else with that. Put that there, put that there. Let's just see if that actually works for us. So we'll come up here, take a look at our wrapper, and nothing. So we'll come back to our generate processor. Class declaration dot functions. Let me try that for the moment just to see if it's actually running right now. So it's definitely running. It's just for some reason not pulling in those functions. Let's see. So filter based on public, not the constructor, doing a join to string. I wonder if, let me change this to a map, because when I'd done this before, I used a map and then a join to string. Why is that not working? What is he not liking here? Oh, that. So join to string, passing in the new line like that. Oh, well, duh. I had to return empty string down. Time to wake up, huh? Let's come back to this. That join to string should have worked, and it would have if it actually wasn't for these meddling kids. Okay, let's do that. Now it should be okay. Oh, somebody doesn't like something. Expecting declarations. Let's take a look at what this thing looks like. So there's some odd thing in there that my bar is getting messed up somehow. Oh, I didn't change this to say trim margin. Now let's try it. There we go. So we have fun save and fun delete. So far so good. Note that I don't have any parameters there, so I'm going to need to put the parameters in as well. Let's do something similar to get the list of parameters as a property. I'm going to call it parameter decals. And so we're going to get our declared functions. And actually, no, this should actually be on a KS function declaration. There he is. So in here, I'm going to say, let me grab the parameters that we have, and I'm just going to join those to string directly. And what this one's going to want to do is actually have the name colon the type. So we're just going to have that be $parameter.name, and we'll do a question mark dot get short name colon $parameter dot type. And the thing with the type that's interesting here is that this type object, if we take a look at it, he is a KS type reference. So that's just basically something saying that I'm referring to some type. I don't have the type information. I just know it's a type somewhere. So I need to resolve that. And resolution here is kind of expensive. So this is one of those things that you probably want to cache as you're doing it, or just try not to do it if you can avoid it. So once I resolve it, I can actually grab the declaration for it and get that qualified name. And then I need to, again, convert him into a string. There we go. And this as string gives you a string name that you want to use as opposed to toString, which is for debugging. So now we should have those parameters. I'm going to join these. By default, join to string joins with commas in between, which is really what I want. So I should get a single string out of this. Now I can come up in here and say dollar function dot, whoops, what did I call that? Oh, let's put a curly in there. For some reason, it's not helping me here. Wait a second, what is function? KS function declaration. That is very odd. Huh, for some reason it wasn't completing that for me. So we'll put that in there as well inside parens. And this is one place where using extension functions or extension properties is really nice. When you're setting up these templates, you can call them just as properties instead of having some code that sets up a string as a variable and then uses it. You can just directly call things. This can be a little bit cleaner. Let's see what happens when we run this. Okay, so we have person, which is a com Java dude person in both cases there. So far, so good. Now, if let's just add another guy in here. Fun count n colon int, just so we can see that it'll work for other types as well. Again, we're not handling generics here. I don't think what I have right now will completely work for generics, but we'll see that n is now a kotlin.int, so that worked just fine. So now let's put the code in there that actually does our calling or our logging function. And we'll take a break in just a moment. I'm almost done with this. And I'm going to say println calling something or other. So that's going to be the same guy I got up here. So hey, maybe we want to say function name equals that. And then I can just make this function name. And then have this be function name. And then we can call, what do we call it? We called it wrapped. Passing in the parameters. Now the parameters we pass in here aren't going to be parameter decals. We don't want to have name colon type. We just want the list of names. So I'm going to take this parameter decals guy, make a copy of him, and just call it parameter names. And we're just going to join to string that part. So we actually don't need to have it inside the quotes. We don't need that stuff. And I'll say otherwise. Oops. We should never get the oops in this case, but we should check for it for real. So inside here, we'll take that, put it in wrapped, and that should be parameter names. And let's see what it generates. Oh, one of the candidates has a mismatch, yada, 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 yada. Oh, I have to say wrapped dot function name. That would help, huh? So wrapped dot dollar function name. Now let's try that. And there we go. So that's basically the code that I wanted it to generate. So now if I actually use this thing, I could say here, repo.save some person, repo.delete the person, repo.count. And if we just use the repo directly, we should just see that the functions are corresponding. If, however, I use the decorator, and this is actually called a decorator. The interface looks the same, has the same functions, but it's wrapping something to change its behavior slightly. Normally, by the way, with a decorator, you'd have an interface associated with this so that both repository and logging wrapper repository implement that same interface. But you don't have to do this. This still has the characterization of a decorator. And let's do a little separator. And we run this. We'll see that I should have put a thing before it as well. Okay, let's try it one more time. There we go. So we now have saved, deleted, and counting is being called. And then each of these has that extra logging built into it just by that decorator. So it's a bit of a contrived example here. Typically, you'll see this thing used for, like on Android, there's this um, framework called Room, which is used for mapping objects into database declarations. And so you'd have those objects have annotations on them to say what they're going to be doing. Is this an entity? Is this a data access object? Do I want to define relations between classes? And also, what type of, when this function is called, what type of squeal statement is run with it. That's SQL for those people who don't believe that squeal is pronounced squeal. So that's one of the cases where you'd really see this used in real life. It's a little more complex example, but basically you're generating code, and that can be super, super helpful. So hopefully this will demystify if you ever see a KSP used or an annotation processor used. Okay, any questions on any of this? Okay, so it's 8:37. Let's come back at 8:47 and we'll talk about the exam. Camtasia on, good. Okay, so any questions on any of that before we move on? Sure, I'll come back to that in 1 second. One thing I wanted to point out here is that I just added a comment in here about the process saying that, make sure you understand that this is really super oversimplified. I have a link to that article that I just mentioned that goes into a lot more detail. I think it does a great job. It's a little bit Android specific in some spots, but not really. Hold on 1 second. My watch is alarm ringing in the other room. I'll be right back. I brought it in here just in case it does that again. I just turned it on, and I guess it's trying to get all its old alarms out of its system. Okay, so reified. Let's come back to here. And let me just go ahead and open up a new file for him. Let's say new file week 13. Okay, so the main thing that we're trying to do with the reified is take a generic type declaration that normally we lose during compilation and be able to have access to it. And what I mean by normally we lose, let's take a look at a function like maybe we have a generic function. Well, let's take a list, for example. If I said val x colon list of string, this list of string here, this type information is only available at compile time. If you take a look at what's in the byte file, it's just going to be list. It's not going to have any type information at all on that. For debugging symbols, it may actually have the list string somewhere, but as far as the compile is concerned, it strips away that words, the string information there, and just assumes that everything's an object in there and that the compiler did all the checking for you. That's called type erasure. And it's a byproduct of how the bytecode behind the scenes worked. When they added in generics, they didn't have support in the Java virtual machine to be able to deal with it. And so the only thing they could do was only deal with the types, generic types at compile time. This ends up affecting other languages that run on the Java virtual machine as well, because you have this type erasure happening. And what happened here, if I had, well, we'll do the same kind of thing that, let me just copy that code out. Here we go. This way, let's be kind of like handy in one separate piece here. And let's copy these guys. And I'm going to change the names on these. So what we have inside here, this new list is going to lose that string information at runtime. So if we tried to take a look at the list and saw what new list is, we wouldn't be able to. The thing that we're trying to do is create a generic function like this and be able to know what T is. Right now, that T information completely disappears when this is compiled down. So inside here, we can't say is something of type T because we no longer have T available. This works at compile time to match up here, 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 and here, and here, so that when this is compiled, the compiler is going to say, hey, yeah, I can control all that. I can make sure it's the same type being used there when I compile this. But at runtime, I won't be able to do that runtime check. So the only thing we could do in this particular case was pass in explicit metadata that describes the type that we're interested in. Now we're chaining that metadata to T so that it actually has this correct linkage through everything, but we have to explicitly pass that metadata in. And so that's where we're passing in this string : class. It would be really nice to use that T directly. The only way to possibly do that is if we had, if we used an inline function. So the T actually gets replaced in line explicitly. That's what reified does. It makes it real, which is what reified means. So when somebody calls list dot myfilters instance 4, like up here, it's going to replace that code in line, and all it needs to do is take whatever type it knew at compile time and put it in each of these spots for T. And then that becomes the code in place. So it basically just takes this code here and drops it in like that, passing in a string here and a string here. And I'm going to say new list 2. And something like that. And the return really doesn't do anything. It's just, it's being used in line. So this code gets dropped in line, and it really just takes the string from here and drops it in everywhere it saw T. So it's just replacing it in line. Does that make some sense? Well, it's at compile time we know what the type is. So the compiler is able to double check things and say, oh, is something of this type, and then set this code, compile this code as it normally would by using this explicit type here that got replaced from the generic type. So it's just really a way of converting a generic type into an explicit type. I'm gonna. Okay, so one other thing I wanted to do, I should have called that week 1301. And then I can create a new file, week 1302. So let's say that we have a function that takes a whole bunch of integers or a whole bunch of strings, and we might want to help to differentiate those. Instead of them just being strings or ints, we might want to actually give them a real type. So if we had a I don't know, plot line. Well, this isn't what I wanted to do with that. Let's say explain person, why not? But instead of having a person object here, maybe we had a whole bunch of separate pieces of information, like name, string, favorite, color, string, age, int, number of friends, int, maybe number of working eyes, int, maybe a height, int, something like that. And there's a whole bunch of just ints here and strings here that you could put in a wrong value. You could get the order of it wrong. You could have something that, the units get lost. In this case of height, int doesn't have any unit attached to it. So what might be desirable would be to wrap all these values, each independently as a different type, just so you can explicitly qualify it. So if we had something like class color, which is just going to be a wrapper around a string, something kind of like that. Then we could replace this by color. And now we actually have a type that we can attach functions to. We can use as though it's an object, as opposed to a really trivial object like a string. And it's impossible for somebody to pass in a string and get it wrong. One of the things, I don't know if I mentioned type aliases. You can define something called a type alias. We could have this be, I'm going to call it color1 equals string. So you could define something like this, a type alias, and this is just an alternative name for string. So in a case like this, if I said explain person2, where favorite color takes in a color1, that's still a string. I can still call this explain person blump blump explain person2, right? Yeah. I can still do something like that, right? Notice I'm still passing in a string, even though this says color1. Color1 is just an alternative name. And sometimes that's useful, but if I created an actual class for it, I can't pass in a string there. I actually have to pass in a color with some string value. And that's nice because we're providing a little extra type safety here so that you can't get wrong values. And you could add extra functions to it if you wanted to, or extra properties, like val length of color name, which is an int. And then we could say get equals value.length, something like that. You can do, basically treat it as any other object. The problem, though, is this is a lot more expensive than just having that string, because now you have a whole nother object that you have to create and then get garbage collect later on. Kotlin provides something called an inline value class that basically makes it look like you've wrapped this thing and gives you all the same type of functionality, but you don't get the expense of having an extra wrapper object. It only works if there's a single value that you're using, and you can call that value anything you want. You don't have to call it value. But I can call this value class. I'm going to call it color val. And what is he unhappy about there? Oh, I have to put the JVM inline. This is an annotation that adapts it for use with Java. So what this guy does, the value class, anytime you say that, it creates an inline class. This is one that anytime you use color val, it's just going to replace it directly with whatever this value is. Well, color value.value. And you can have functions just like this. It'll work just fine. So if I come down here and say color val, I get the same benefit with number 4. Oh, I still had that calling 3. So I get the same kind of benefit of having a type safe value here without the expense of actually having another object wrapping around it. So this is something that there's places where this may be useful from time to time. Um, I haven't used it yet, but it's one of those things that once in a while, maybe it's going to be helpful. Um, so that's just the one last little thing I wanted to hit real quick was this idea of a value class. Any questions on that? Okay. The big difference here in either of these cases versus type alias, I'm not really a fan of type aliases. One of the places people tend to use it is for function types. I would much rather see the function type directly. It's one of those things that, when you're first learning the language, sometimes it feels like, oh, if I could just give a name to that function type, it'll make more sense. Once you're used to the way function types look, then it's easy enough on its own. Okay, any questions on anything there? Okay, so now at this point, I've covered everything that I wanted to cover. Does anyone have any questions on anything we've covered the second half of the term? Because the second half of the term content is what's going to be on the final. Anything that felt fuzzy? Okay, well, we still have one office hours between now and the final. So if you think of questions, feel free to pop in on Tuesday and you can ask away. Other than that, I will have the test set up the same way that I did before. Hopefully I'll get it actually set up the same way I did before. And then you can take that and be done with the class. Yay! A little note on the exam scores. Right now, they're scored from 100 points, and I have to convert that down to the 4-point scale. The 4-point scale is going to be a little different based on the 100-point scale. The letters there, A, B, C, D, F, are your normal 100-point scale A, B, C, D, F. And so I have to convert those into the 4 points. So there'll be a little bit of a difference on how you see that at the end. Unfortunately, Canvas doesn't let me do that automatically. So I'm just going to have to put that in a spreadsheet and calculate it. But if you just take a look on that and convert that 100-point scale to A, B, C, D, F via the normal way that it would be done in any other class here, then take those letters and convert them back to the 4-point scale. That'll be what matches up for the class. I don't think it's going to affect anybody in a negative way, but just as a heads up that it's not going to be the score that you're going to see in the grade book for your final score isn't quite going to be right. Okay, any other questions? Cool. Well, there's no assignment tonight because this is now study time for the exam. Study away. Let me know if you have any questions, and good luck on the exam.